In this problem solving session number 3, we are going to solve some problems based on lecture 7 and 8. Here the first problem, you are asked to prove that trace of rho is equal to 1 and you have to use the general definition of the density matrix. This problem, actually we have proved trace rho is equal to 1 using the definition of the density matrix for pure state. Now we are going to use the general definition. The general definition of the density matrix or the density operator is this: rho is equal to sum over p alpha. P is the classical probability, k psi alpha, bra psi alpha. And let us now take the trace. So trace of rho is going to be basically the sum over the diagonal elements of the density matrix. So it is taken over the basis state k, say k rho k, right? So this is the sum of the diagonal elements. Now let me open it up, sum over k here, and let me now write the density operator or the density matrix definition: sum over alpha, p alpha, k psi alpha, bra psi alpha, and then I have here k. Okay, now you see these basis states, these are k, these are basically basis states, because you have to take the when you take the trace, you are taking it over the basis states. So, and psi alpha, k psi alpha, this is an arbitrary state, so we can always write it as a superposition of the basis state. So we can write summation sum over I ci ket I. So ket I are the basis states, and similarly I can write its counterpart, the bra psi alpha. For that I can write it, let us take it as sum over j, and it would be cj star, complex conjugate of the amplitude, and then bra j. Okay, again ket j is basically the basis state. Now if I put ket psi alpha and bra psi alpha here in this expression for trace rho, okay, and if I do the analysis, let me do that. Trace rho is equal to, I have sum over k here, sum over p alpha. Now for k psi alpha, that is sum over I ci ket I, and then for the bra part I have sum over j cj star bra j and k. Now you see this is the scalar product between j and k, and this is nothing but Kronecker delta jk. And using the property of the delta jk, as you know, delta jk is equal to 1 if j is equal to k, and it is not equal to it is equal to 0 if j is not equal to k. So using this, I can now write here it as sum over, let me take this summation here, sum over p alpha outside, and then I have sum over k here, and using this property, if I put just j is equal to k, then I will have sum over I ci, I will have, it would be ci, and j is equal to k I am putting, so it would be ck star, and I have also here I, right, ket I. Okay, now again you see these are just numbers ci and ck, so I have the scalar product of k and I, that's going to give me delta ki. So I will be now having sum over alpha p alpha, sum over k, let me take the summation sign here, ci ck star here, and this scalar product of k and I is going to give me delta ki, Kronecker delta. Again using the property of the Kronecker delta, what I am going to have is sum over alpha p alpha, sum over k ck mod square. Okay, and you know Ck is basically the quantum probability amplitude, and its mod square, if you sum over all the amplitudes, it is going to square of the amplitude, it is going to give you 1. So you will be left out with sum over alpha, p alpha, and that is basically the summation of all the classical probabilities, and that is equal to 1. And thereby you see that we have the general proof we are now getting, that trace rho is equal to 1. Now let us do the second problem. So in the second problem, you are given a 2 by 2 matrix. 1/2 and 1/2 are the diagonal elements, and I by 2 and minus I by 2 are the off diagonal elements. The first part of the question is it a density matrix? Second question is, if so, what is its purity? And thirdly, find the expectation value of sigma x in the state rho. Because you know, if it is a density matrix, then the state of a quantum system is represented with a density operator. So you are asked to find out the expectation value of sigma x in the state rho, and sigma x is the x component of the Pauli vector or Pauli matrix. Now the part B and part C of the problem depends on the fact whether the given matrix is a density matrix or not. Okay, to do that, let me just remind you first of all about the some properties of the density matrix. So you know that the essential properties of density matrix, by which we can say a matrix is a density matrix, are as follows. Firstly, this density matrix has to be Hermitian, that means rho should be equal to rho dagger. And then second property is trace of rho should be equal to 1. And thirdly, which is very important, is that eigenvalues of a density matrix must be non-negative, and it is related to the fact that the diagonal elements represents probabilities, and probability cannot be negative, so eigenvalues has to be non-negative. So this is critical. Now let us check these properties one by one for the given matrix. Firstly, what about the hermitativity? That means if we find out the rho dagger, then it is basically first you take the complex conjugate of the matrix and then you take the transpose. And if you take the complex conjugate of the matrix, then you will have 1/2 minus I by 2. Just once again you see that this is what our matrix is. So if you take the complex conjugate, I have here minus I by 2. Here I am going to have I by 2, and it would be half. And then if you take the transpose, then rows become column become rows. So you have 1/2 here minus I by 2, I by 2 half, and this is exactly the same as the density matrix rho. So that means rho is Hermitian. So first property is now satisfied by the given matrix. Now what about the other two? What about trace rho? Trace rho is the sum of the diagonal elements, 1/2, that is equal to 1. So this second property is also satisfied. And thirdly, what about the eigenvalues? To find out the eigenvalues of rho, we have to solve the characteristic equation, and you know how to set up a characteristic equation. You have to just your density matrix is there, so just set up the characteristic equation by this way. You have to find, I think all of you know how to set up a density matrix equation, a characteristic equation. So this is what you have, and if I open it up, I have this minus 1 by 4, right? This is equal to 0, or I can write this is as lambda minus half whole square. If I take it this side, I have 1 by 4, or I have lambda minus half is equal to plus minus 1/2 if I take the square root, and then that means I have lambda is equal to 1/2 plus minus 1/2, and this gives me two eigenvalues. One is lambda 1 is equal to half minus half, and lambda 2 is equal to 1 half plus 1 half. That means I have lambda 1 is equal to 0 and lambda 2 is equal to 1. As you can see that both the eigenvalues are non-negative. It implies that eigenvalues are non-negative. That means the third property is also getting satisfied. That means what? That means that rho is a density matrix. The given matrix rho is a density matrix. So this answers our first part of the question. Now what about the second part? Second part, it is asked what is the purity of the matrix. So you know the purity is actually defined as P is equal to trace of rho square. Trace of rho square, if you find out, it gives you the information about whether the density matrix represents a pure state or a mixed state. And we have already discussed it in our lecture class. So let us find out what is trace of rho square. Now to find that out, first let me find out rho square. So it's multiplication of the density matrix rho into rho. So rho is equal to 1 half I by 2 minus I by 2 1 half, and then I have another row 1 half I by 2 minus I by 2 1 half. Now you please multiply it. Then if you do the matrix multiplication, this is going to give you simply 1 half I by 2 minus I by 2 1 half, and this is nothing but the rho. Okay, this means rho square is equal to rho, and that means that trace of rho square is equal to trace of rho, which is equal to 1. So trace of rho square is equal to 1. So purity is 1. Okay, now the third part, you are asked to find out the expectation value of sigma x component of the Pauli vector. And you know that expectation value of an operator can be worked out by taking the trace of the product of rho and the operator. So you just have to find out trace of rho into sigma, and sigma x is its representation is 0 1 1 0, right? That is sigma x. So let me find out what is rho sigma x. Rho is equal to 1 half I by 2 minus I by 2 1 half, and sigma x 0 1 1 0. If you do the multiplication, you will have I by 2 1 half minus I by 2, and this means the trace of rho sigma x, just add the diagonal elements, you will get I by 2 minus I by 2, right? If you add it, so therefore you are going to get 0. So that's the expectation value of sigma x. Okay. Now let us do a somewhat similar problem. Given a 2 by 2 matrix, its diagonal elements are 3 by 4, 1 by 4, and off diagonal elements are 1 by 4 and 1 by 4. The first part of the question, does it represent a density matrix? Then second part, if so, what is its purity? Third part, find the expectation value of sigma z, where sigma z is the z component of the Pauli matrix or the Pauli vector. So let us do it. So already you know that if the matrix has to be a density matrix, it has to obey some properties, as we have already discussed. First of all, what it should have, that rho should be equal to rho dagger. That means it has to be Hermitian, and you can immediately actually see, because rho is given as 3 by 4, 1 by 4, 1 by 4, 1 by 4, and if you take the complex conjugate, and because all elements are real, so complex conjugate will give you the same thing, and if you take the transpose, and you are actually going to get the same matrix as that of rho. So therefore rho dagger is equal to rho. Okay, so the first property is satisfied. Then next, trace of rho is 3 by sum of the diagonal elements, 3 by 4 plus 1 by 4, that is going to be equal to 1. So this property is also, second property is also satisfied. And thirdly, now let us find out the eigenvalues. to find out the eigenvalues, you just have to solve the first set up the characteristic equation, then solve it. So I have the characteristic equation. Let me set up 3 by 4 minus lambda 1 by 4 1 by 4 1 minus 1 by 4 minus lambda is equal, determinant is equal to 0. From here I can get, you please do it, you will get the equation. This characteristic equation will be lambda square minus lambda plus 1 by 8 is equal to 0. And if this is a quadratic equation, so its solution would be lambda is equal to, here I have 2, then 1 plus minus, you will have 1 minus half, okay, b square minus 4ac, if you see that. Okay, so this is going to give you, here you will have 2 1 plus minus 1 by root 2. So the eigenvalues are, two eigenvalues you will get. Lambda 1 is equal to 1 half plus 1 by 2 root 2, and another one is lambda 2 is equal to 1 half minus 1 by 2 root 2. As you can see, both the eigenvalues are both eigenvalues are non-negative, so therefore it satisfies the third property as well. This implies, I can conclude that rho is a density matrix. So now let us do the second part of the problem. So you are asked to find out the purity. To find the purity, you just need to find out trace of rho square, and rho square, just take the matrix multiplication of rho into rho. So rho is 3 by 4 1 by 4 1 by 4 1 by 4, and another row 3 by 4 1 by 4 1 by 4 1 by 4. So if you do the mathematics, so let me just write down the finally what you should get. Simple matrix multiplication, you will have 5 by 8 1 by 4, please verify yourself, 1 by 4 1 by 16, and this is what you have. So now what about trace rho square? Sum of the diagonal elements, 5 by 8 plus 1 by 16, so this is going to give you 11 by 16. So this is basically your purity, and as you can see, this is not equal to 1 and it is less than 1. So that means, so rho represents a mixed state, right? Because trace rho square is less than 1, so it represents a mixed state. Now third part, you are asked to find out the expectation value of the sigma z. Sigma z would be, just you have to take the trace of the product of rho and sigma z. You know that sigma z is 1 0 0 minus 1. So if you take the multiplication of rho into sigma z, so rho is your 3 by 4 1 by 4 1 by 4 1 by 4, and sigma z is 1 0 0 minus 1. If you take the product, that is going to give you 3 by 4 1 by 4 minus 1 by 4 1 by 4 minus 1 by 4. Now that means that trace of rho into sigma z is equal to sum of the diagonal elements, and actually this is your expectation value of sigma z, and that is going to be equal to 3 by 4 minus 1 by 4, and that is nothing but 1 half. Now let us do this problem. This is an important problem related to optical block equation. You are asked to solve the optical block equation in the steady state condition, that is when t tends to infinity. It actually means that you have this two-level system which is interacting with the classical light field is there, and you wait for long enough. That's what it means by t tends to infinity. And you are asked to find the steady state excitation and steady state coherences. I'll explain what I mean by steady state excitation and steady state coherences. So let us solve it. To do that, first let me write down the optical block equation again. We have done it in our lecture number 8. So optical block equations are delta rho tilde EE delta T, please refer to lecture number 8. There we have done it. So let me write here. It is I capital omega by 2 rho tilde EZ. Rho tilde EZ and rho tilde ZE, these are coherence term. And I have gamma rho tilde EE. Rho tilde EE refers to the excitation. And then for the ground state, I have delta rho tilde ZZ delta T is equal to minus I omega by 2 rho tilde EZ minus rho tilde ZE plus gamma. Gamma is the decay rate as we have discussed, rho tilde EE. Then for the coherence terms, I have delta rho tilde ZE delta T is equal to minus gamma, small gamma perpendicular suffix you have here that refers to the transverse decay rate, plus I gamma rho tilde ZE minus I capital omega by 2. Capital omega is the Rabi frequency as we know. Rho tilde EE minus rho tilde ZZ. And then I have delta of rho tilde EZ. It's basically complex conjugate of the previous equation. Then you will get this equation. I have gamma perpendicular minus I delta rho tilde EZ plus I omega by 2 capital omega by 2. We have rho tilde EE minus rho tilde ZZ. Alright, so this is what I have. Now in the steady state, let me do it systematically. In the steady state, first let me set rho tilde delta rho tilde EZ delta T is equal to 0, right? And also I'm going to use this fact that rho tilde EE minus rho tilde ZZ, I can write it as rho tilde EE minus 1 minus rho tilde EE, because you know rho tilde EE, these are populations, rho tilde ZZ is equal to 1. So using this, I can write rho tilde EE minus rho tilde ZZ as 2 rho tilde EE minus 1. Okay, this I am also going to use. So now let me set delta rho tilde EZ delta T is equal to 0. Let us just see this equation. From this equation, you can now write rho tilde EZ. Now in the steady state, that means T tends to infinity. By setting this, actually you mean that you are going over to T tends to infinity, then delta rho tilde EZ delta T is equal to 0. And from here, from this equation you can easily find out what is rho tilde EZ, and that's going to be very trivially, you can see that this is going to be I capital omega gamma perpendicular minus I delta, and you have rho tilde EE minus half. Okay, where I have utilized these relations as well. Okay, here I have utilized this relation. That's the reason I am getting it. If you take a piece of paper and a pen and please do these things with me, then you will get it very easily and straight away. And this, from here I can write it. Let me write it in a more simplified way. Rho tilde EZ T tends to infinity is equal to, if I can just do this, gamma perpendicular square plus delta square, and here I multiply the numerator by gamma perpendicular plus I delta, and if I take the multiplication with I capital omega, I am going to get here omega delta minus I gamma perpendicular, very easy to see, and this part will remain as it is, rho tilde EE minus half. So this is what I have, one equation. So let me say this is my equation number 1. Okay, now if I take the complex conjugate of this equation, then I am going to get rho tilde ZE as well. That is this, I am going to get it would be minus capital omega delta plus I gamma perpendicular divided by gamma perpendicular square plus delta square, and it would be rho tilde EE minus 1/2. So this is another equation I get. So you see, I am already getting the steady state coherences from these equations. Now what about the populations? To do, actually now let me use equation 1 and 2. Using 1 and 2, I can find out what is rho tilde EZ minus rho tilde ZE as t tends to infinity. That means in the steady state. This I will require because I want to find out now rho tilde EE, and there this particular term is there. So that's the reason I need to know this, and I can get this just by using equation 1 and 2, and you will get it as, if you just subtract them, you will get 2I capital omega gamma perpendicular divided by gamma perpendicular square plus delta square, and you have rho tilde EE minus 1/2. Okay, so let's say this is my equation number 3. Okay, now let us say in the steady state, let me set delta rho tilde EE delta t is equal to 0, and this will give me, this is going to lead me rho tilde EE is equal to, okay, let us look at this equation once again, because now I am setting this on the left hand side. If I take it to be 0, from there I can find out rho tilde EE, and rho tilde EE would be 1 by gamma I capital omega by 2 rho tilde EZ minus rho tilde ZE. Now rho tilde EZ minus rho tilde ZE, these are the steady state values I have to put. So therefore I have excited state steady state population, or the density matrix element referring to the excited state is this, t tends to infinity. I have, if I put the values of rho tilde EZ minus rho tilde ZE, and I will get it as omega square gamma perpendicular divided by capital gamma perpendicular square plus delta square, and here you have rho tilde EE minus 1/2. Okay, this is what you will have. And okay, now you have to solve this equation. This is simple algebra, just shuffling the terms. You should find out rho tilde EE. To do that, let me just do it this way. Rho tilde EE is equal to, say, alpha rho tilde EE minus 1/2, where alpha is equal to minus capital omega square gamma perpendicular by this gamma divided by gamma perpendicular square plus delta square, and from here rho tilde EE is equal to minus 1/2 alpha divided by 1 minus alpha. Now if I put the values of alpha, this implies rho tilde EE as t tends to infinity in the steady state. I will have capital omega square divided by twice gamma perpendicular capital omega gamma, this is your gamma. And if you just do the mathematics, very straightforward, you will get 1 plus delta square divided by gamma perpendicular square plus capital omega square divided by gamma perpendicular capital gamma. Okay, this is what you will have, and this is your steady state excitation. So this is your steady state excitation. Steady state excitation. Now if I put this rho tilde EE in equation number 1, I am going to get the steady state coherence rho tilde EZ as t tends to infinity. That's the steady state coherence. Steady state coherence. I am going to get the expression I capital omega divided by 2 gamma perpendicular, and in the numerator I will have 1 plus I delta by gamma perpendicular divided by 1 plus delta square gamma perpendicular square plus capital omega square divided by gamma perpendicular capital gamma. Okay, this is what my steady state coherence is. So let's say this is my equation number 5. In fact, what we can do is that we can write these equations number 4 and 5 in a simplified form if we define a parameter called S, which is known as the saturation parameter. If I denote this bunch of parameters, capital omega square divided by gamma perpendicular capital gamma divided by 1 plus delta square divided by gamma perpendicular square. This is known as saturation parameter. This is known as saturation parameter, and it is proportional to capital omega square. That's the Rabi frequency, and you know the Rabi frequency is proportional to the electric field amplitude. That means capital omega square is proportional to intensity. So therefore saturation parameter is basically proportional to intensity of the light field. And using this parameter, now I can write my steady state excitation rho tilde EE as, in a very simple term I can write simplified way, S by 2 divided by 1 plus S, where small s is the steady state is the saturation parameter. And also I have rho tilde EZ, that's the steady state coherence. In fact, if I take it mod square, that would be easy to write actually. Then I will have gamma divided by 4 gamma perpendicular into S divided by 1 plus S square. Introduction of the saturation parameter is very useful because, for example, you can see from this expression that when the intensity is small, that means, as you know, S is directly proportional to intensity. When S is small, then excitation is proportional to increases. This excitation rho tilde EE, it increases linearly with S when S is small. However, as you can see, as S tends to infinity, that means if the intensity become very large, then you just look at these expressions once again, you will see that for very large intensity, that means S tends to infinity, rho E tilde tends to half. And what it means? It basically means that the largest excitation which is possible when intensity is too large, largest excitation is half the population. And it makes sense because if you have studied laser physics, there you know that maximum population, if you increase the intensity of the the field, for the case of a two-level atom, the maximum population that can be achieved is only the 50%, right? And because of this reason, the two-level system cannot be used as a laser.